All right, class, welcome to chapter 4. Chapter 4, let's see, we started probability chapter 3. We learned a lot of good stuff here about just counting cards, right? Dice. Let's see, let's kind of think back to our chapter 3 events here that happened. One was independent or versus dependent, right? We got to think about that. We got to think about mutually exclusive versus non-mutually exclusive events, right? We got to think about that. The rules that we learned were just the basic concepts of probability. And then we learned something called the multiplication rule. You guys remember that, right? You multiply things to get possible events. And then we learned the addition rule, and we gotta make sure we keep those straight in our heads, and we have to ask the questions before we can use them. All right, and then we learned about permutations and combinations, right? That's kind of the next step that we got to. So hopefully you got the homework on that. Hopefully you got all that good stuff here. And then there was 3.4. It was called the additional topics, right? So we got that kind of towards the end. I think kind of got really crazy because we did combinations, permutations within probability. So if you survived 3.4, you did really good. Then we move on to chapter 4. So we're going to go probability, and then we're going to add in the word discrete. Now, the word discrete in mathematics does not mean in the word in English, right? It means discrete, meaning like you don't tell everybody, you just kind of tell a few people here and there, you're being discrete about something. In mathematics, it has a different meaning. So it has the meaning of things that are only be counted. So like 1, 2, 3. It's not like 3.5 hours. Look good? So discrete, it's individual pieces. And the way we normally count them is by whole numbers, sometimes integer values. We can kind of do that, but in this case, it's going to be just whole numbers. We're counting specific items, and you can only have whole pieces of those items. So a good example would be number of kids in the family. That would be a discrete item, right? You can't have 2.5 kids. You can have 1 kid, 2 kid, 3 kid, 4 kids, yes, but not 2.5. Okay, so that's what the word discrete means. So now the question is this: how do we build a whole structure of probability based upon discrete numbers? Okay? You're just counting things, right? Counting kids in a family, counting the number of cars that households have. Maybe that would be a good example too, right? 1, 2 car, 3 car, 4 car. So let's get started. Let's go with it. Chapter outline real quickly would be probability distributions. We're going to talk about that. Then we're going to talk about binomial distributions in 4.2 if we get there today. And then of course 4.3, the last one is just here's some more stuff that we haven't covered yet, kind of like chapter 3. So let's go with it. 4.1, probability distributions. If you want to take notes, go for it. The highlighted sections are the ones I've put in highlights so that you know at least what's kind of the more important stuff you should write down, and the stuff you don't need to write down as much. All right, let's get some definitions now. So probability distribution, some definitions. First things first is all right, first thing is the random variable. And so we're going to build our definition here. First of all, what is a random variable? Represents just a numerical value associated with each outcome of a probability distribution. So we want to see 3 phone calls made during the year. We're looking at households with 2 children inside it. We're looking at households with 3 cars. That's kind of what we're looking at, that variable. And what we do is we have to give it a variable name, obviously. There. Okay. Oh, go backward. Denoted as X. So that's the X value. Now we're going to denote. Okay, so that's the broad definition. Random variable is just an X we associate. We've been doing that all this time, right? We've been saying that what happens if you roll a die and you get 4, right? So 4 is your randomized variable. What we want to do in chapter 4 is now to go on to the discrete random variable. So now this is where we're at in chapter 4. Just a slight different change here. Discrete random variable says this. It's a variable, but has a finite or countable number of possible outcomes. We can actually even list them. Whereas opposed to if you look at miles per hour or hours in the day, you can chop that up and you can't count it anymore. Because you can have let's do the distinction here. I guess that'd be the best way to do it. Distinction between a discrete random variable. As you're writing down the definition, let me give you the example. So there it is. There's a number of sales calls that a salesperson made in one single day. Notice he can't make 2.5 phone calls, right? That does not make sense. He's either going to pick up the phone and dial, or he's not. So this becomes a discrete random variable. And so there it is, 0, 1, 2, 3, 4. So X is the number of sales calls. Cool. X would be the number of children in a household. X would be the number of cars in a household. So there it is. Okay, contrast that. And you guys tell me if I'm going too fast, okay? I don't need to write down the example because you'll have enough, but at least the highlighted section here. The continuous random variable, that's the contrast here. Now the discrete random variable is uncountable. I can't start counting all the way up. Normally what we do is we represent it by an interval on the number line. So we go from here to here. All right, let you write it down. Go with it here. Okay, good example would be, now we have the hours spent on sales calls in a single day. Notice it's an interval, so it has to actually stop somewhere, right? 24 hours in a day has to stop there. But the number of hours, the reason why it's not countable or uncountable, as we say, is because the person can spend 2.5 hours, correct? Or 2.52 hours. Let me write it out just so we have kind of the understanding here. The reason why it's not countable is this marker right here. I put a little dash here, right? So we can break it up into infinitely many pieces. That's why it's uncountable. So if we say like, hey, that's he spent 2.4 hours on the phone. Well, did he spend 2.4 hours? Did he spend 2.43 hours on the phone? Did he spend 2.43 hours, or did he spend 2.435 hours on the phone? Right? You can make this into like a whole infinite list, right? Just that one piece there. So we say that's not countable, but the number of phone calls he made, that's countable on a certain, or in a certain interval of time. So that's kind of the difference there. All right, just so we got that distinction in our heads, let's go. So you guys tell me, don't need to write it down, just kind of think with me here. So tell me if this is a random variable, is discrete or is it continuous? Just a quick answer, all yours here. So X is going to be represent the number of Fortune 500 companies that lost money in the previous year. Discrete or continuous, all yours. Can we say that 3.4 companies lost money? No. The number of companies, we can say like 4 companies lost money last year, or 112 companies lost money, right? But 112 and a half of the companies lost money. No, that does not make sense. Splicing it in half does not make sense. So perfect. Solution is, it is a discrete random variable. It's individual points. They are isolated from each other. You count them by whole numbers. Okay, does that make sense? Good, then I'm glad here as we make distinctions in our heads. Clarifying definitions is a good thing. Okay, this one, all yours. Talk to me, don't need to write it down, just gonna talk to me. Number 2, X represents the number of gallons in a 21-gallon tank. Discrete or continuous? Continuous, right? I can break up gallons into 10 and a half gallons, right? 10.3 gallons, 10.32 gallons. Yeah, I can break that up. So this guy is a continuous random variable. Notice it is still an interval, right? The most you can have is 21, right? But what we do is we kind of fill in the number line because we can have portions of a gallon, no problem. Okay, that's continuous on us. Okay, now let's jump to, let's put things together here. Now we have the word discrete in our minds. Well, now probability, we know, right? Probability is the fraction or a decimal understanding of what can happen. And we have ourselves a distribution. So first things first, probably should write these down, I guess. Yeah, so it lists each possible value of a random variable that can take place together with the probabilities. Has to satisfy these 2 conditions. First of all, the probability has to be between 0 and 1. It can't have beyond 1, can't be a negative. That doesn't make sense for a probability distribution. All right, the sum of all probabilities is 1. So if you add up all the probabilities, they should give you a 1. End of the day. So there's your 2 sort of mechanical definitions of what has to happen in order for this to be a discrete probability distribution. And what happens usually, you know how it says in words underneath here? That's kind of cool to have. Normally when we're talking about this, we just put in symbols. It's a lot faster to write in mathematics. And if you know the symbols, it's just the shorthand way of writing stuff, right? That's what we do in math. Lots of writing here, lots of writing on this one. I think there'll be the most amount of writing on a one particular slide, I think. I just want to make sure we get the correct definition and the restrictions on them or conditions. Okay, tell me when you're done writing. We'll go on. And so for probability, because yeah, that word inclusive means you can have the 0 as a probability, you can have the 1 as a probability. That's no problem there. Okay, the sum have to equal that. Just real quick here, before we get into the nitty gritty of it, let's just talk about. Do I have it on here? Oh, no, I think we're just going to go to it right now. So let's go to. I'm going to skip this one right here. This is kind of just how you make it, but we're going to make it a little bit later here. Here's an example of it. So industrial psychologists administer personality inventory test for passive aggressive behavior or traits to 150 employees. So each individual was given a whole number score from 1 to 5. So 1 is being an extremely passive person or having passive traits. 5 is being an extremely aggressive person. A score of 3 indicated neither trait. That's cool. The results are shown, and there it is. Look at that. There's a constructed. Actually, no, there's a score on it right here. We're going to have to construct a discrete probability distribution from this. So let's do that. So first things first is all we really need. This is frequency right here, and I want probability right over here. That's the difference there. So first things first, though, let's talk about it. Is this, first of all, a discrete data? Is this discrete data? Absolutely. You can't get a score of 2.5, right? No, you either get a score of 1, 2, 3, 4, or 5. That's it. And so that's what makes it a discrete data. Next is, let's go with frequency. Frequency is given here. So now the question is this: what's the probability of a person scoring a 1? What should we do to make that happen or compute that?
That frequency out of the entire frequencies.
Yeah, and how many is the entire frequency? What's the summation here? 150. It said so, right? We can check if we need to, but there's 150 right there. Summation of all the, I should say summation of F is that. Okay, just to make it a probability, all we do is we're going to take this 24. We're going to divide it by 150, and that will make a probability distribution for us at that point. That's it. That's the only change. You guys remember in chapter 2, we did a frequency distributions, right? That's kind of where we started in chapter 2. I think it was chapter 2.3 or chapter, oh no, 2.1. We did frequency distributions. Okay, so let's go with it. So for each one of these guys, we're gonna have to do this here. 24 over 150 gives us 0.16. And then if you want to go back to the next one, 33 over 150 gave us 0.22. And we could do for each one right here. So 0.28, are we good there? 0.20 and then 0.14. And again, those that, I'm just going to do an example. I figure you'll have homework questions like that as well. You can also go back to the video if you need to and stop it and try to do it yourself if you kind of need more of the tactile sort of things there. So all we do is we replace the F or the frequency really just with the P of X. So there's my 1.6 or 0.16, 0.22, 0.328, and then so on and so forth. So about maybe 30%, right? 30% of the people have neither trait here, and then you got a little more of the extremes. So about 15%. Then the question is that the same thing as in society's total, right? Is that just a certain company? Is there a company atmosphere that produces that sort of response? And there's the rest of the questions that could be asked. Okay, so there's that. Next thing that we do with this information is we take it, and the first question is this a valid discrete probability distribution? Let's see what it has to do. What's the two conditions? What's the two conditions for discrete probability distributions?
Between 0 to 1.
Perfect. Are all these little guys between 0 and 1?
Yeah.
Absolutely. It's the first one. Next. Do these guys all add up to 1? When we add this up, will that give us a 1? And now we have to check. Since we divided by 150, we can check it. But yes, eventually, if you add all these different pieces up, you get a 1. Perfect. It has fit our distribution definition. It is a valid discrete probability distribution. Perfect. Okay. Since it is that way, we can do the next step is we can graph it. And do you guys remember from chapter 2, we had graphing stuff. This guy is called a histogram, right? It's basically bar graphs with numbers on the bottom, and these guys connect to each other, right? Because there's numbers. And so notice a few things here. The score, we have to retain that data. Notice the probability is now what's up over here. And so we have 0.15, and kind of notice also that it's kind of rounded, isn't it? We would say this is close to being a normal distribution. It's kind of nice. It pops up in the middle, and the sides are kind of sort of, for the most part, symmetrical. Okay, all yours then. Let's do some more here. This one would be an example just to try out, just to make sure we get our definition straight. So question is this right here. Is this a normal or a discrete probability distribution? Has to fulfill two categories, right? So first things first, we're looking at the probabilities themselves. Are they between 0 and 1? That's the easy one to check. Fulfills, done. Can you guys add them up? See if it gives you a 1 real quick here. Since we have calculators, we can probably do this quickly. Yeah, it does. Absolutely. So even though it's a 3-day forecast, right? So that should not technically, because if it's raining for 3 days, the probability of rain is going to be 90% or 89%, right? So notice it's a mechanical definition. It's not a theoretical definition, right? Where it's like, look, these two conditions met, are the numbers met? So absolutely. So we look at them here. Each one is between 0 and 1. Perfect. They add up to 1. Yes, that is technically called a probability distribution. It would not happen if you added one more day to this. We're good? Does that make sense? Okay, next. How about this? Yes or no? Yep, so we check one works just by looking at the numbers. Version 2 works by adding up the numbers. Or condition 2. What does it add up to?
1.07.
Yep, as we add these guys up, it turns out into a 1.07, which is greater than 1. Who cares? It's not 1, right? It could be less than 1. That'd be a problem too. So in this case, this is not a probability distribution. It does not fulfill criteria 2, right? In that way. Okay, how about this one? One more, and then we'll get going here just to make sure we see things that are and are not. So let's jam with this one here. What do you guys say? Is this
that goes past the.
Yeah, it's not going to fulfill criteria 1 at this point, correct? Tell me the X values that don't make that happen.
5/4 and the negative.
Absolutely. This guy here is above 1, 5/4. That's not a probability distribution at that point, right? And you can't have negative probabilities either. So it fails criteria 1. P3 and P4 are values that are not between 0 and 1. We don't even need to check the second criteria. Who cares, right? Because it doesn't fulfill one of them. It's not going to fulfill. We don't care if it fulfills the second one. Okay. So now that we got our handle on distributions, we saw an example as well, and we know our criteria. Let's get into the math of it here. So we have ourselves this. How do you find the average? How do you find the mean of these distributions? You can't just add them up, divide by how many there are, because they're inside a table. And so because they're inside a table, we're going to just start multiplication. We're going to start a multiplication process of it. So all we do is we take the X value and we think about how many times the X value occurs, which is the probability. We did the same thing for frequency distributions. If you guys remember back to chapter 2, remember how we multiplied the X value times how many times it occurred, right? That was a quick way to find the average. All right, do we need to go back and revisit that real quick here or no? What do you guys say? Up to you guys. Yeah, let's go quickly review here. So let's say this, what's the average of 3? This is just my data, raw data. So I have 4 3s, right? And 2 5s. So I could add them up. Let's see. If I add these up, it would be 16, 17, 18, 19, 20, 21, 22. Everybody okay with 22? As a summation? 1, 2, 3, 4, 5, 6. 22 divided by 6. What'd you guys get on your calculator? So if I were to add this up the old way, right?
367.
3.67, yeah, if we did it like this and divide by how many are there?
Oh, it's just 6.
Just 6, okay. So it's gonna be 3 plus 3 plus 3 plus 3 plus 5 plus 5 divided by 6, we're good? Okay, then we did something called frequency distribution. Remember that? We had a table and we said, look to ourselves, hey, you know what? There's the X and this is the frequency. So what happens here at 3 occurs how many times? 4 times. The 5 occurs how many times? So all we get to do in order to figure out the average, instead of counting 3 plus 3 plus 3 plus 3 plus 5 plus 5, we could just multiply these guys together, it gives us 12. Multiply these guys together gives us 10. And by the X times F, a lot easier to getting us this guy. Then in order to get the mean, we just divide it by 6 and we get ourselves 3.67. Okay, that's what we did there, okay? Here what we have is we have a probability distribution. So this frequency, instead of being a frequency, it becomes how many times this happens, right? But still the same process. All we're gonna do is we're gonna just multiply them across. That's the easiest way to find a mean when we have a frequency or probability distributions. Okay, so let's do an example here. Let's continue with the example that we did about the personality traits. So here's what I got here, probability distribution for personality traits. Those are our numbers, right? We start off with a frequency distribution. We change it to a probability distribution now. That's awesome. So can you guys on a calculator just make a third column? Let's do that. Let's make a third column. We'll call it the X times P of X column. And then once that's done, we're going to just add them up. So that's what this means. The average is the summation of the X times the P of X values. And notice on this one, we actually don't have to divide, right? Remember on the frequency tables, we had to divide by 6. This one, because it's probability, it's the portion of which that time occurs. All we do is we just add them up. We're done. That's so cool. Okay. I will do the tough ones. 1 times 0.16 is 0.16. 2.22 makes 0.44. Okay, I'll do another tough one. How about 4 times 0 is 0.80? Okay, you guys get the easy ones. Okay, and then this is 0.70. Oh, awesome. Okay, Cool. So now let's add them up. Give me the summation of the x times p of x's. And once we do that, then we have ourselves our average right away. So adding them up, all yours.
But
2.94. Awesome. Okay. So notice it's not 3. We don't just grab the 3 because it's the middle of the x's, right? That's not what we want. We want to figure out what's the average of the data itself. So by doing that, voila, we'll get ourselves what we want. So the average should be around 3. The reason for it, because remember when we did our histogram, remember it was, we call it a normal histogram, which means it was symmetric on both sides like that, right? So your average, your mean should be right around 3. And that's exactly what we find. So 2.94 is pretty good. Okay, awesome. That is great. And we can label this as mu. So we should label this mu is equal to 2.94 at the end of the day. Okay, now think back to chapter 2. We did mu, and then we also did something called variance and standard deviation. You guys remember those guys? So let's go with it here. We're going to have two more things here. Remember variance and standard deviation? Standard deviation is just a square root of variance, right? We just take that. All right, let you guys write that down. All right, these are formulas here. And just like chapter 2, it's going to take us a little bit of a long time to get there. Good. We need to build. We need to figure out what the average is, which we just did right now. Oh, sorry, going back. 1 second. We just got that one just now, right? And just like chapter 2, remember how we built the x minus mu column? Then we built the x minus mu squared column. And so we're going to build some columns here. Good. So let's go with it here. So we start off like this. And think with me here, because we are going to I'm thinking, you can write it down if you like, right? Or you can look at the video later and write it down if you like, just kind of do it over again here. So here's what's the average that we had again?
Oh, 2.94.
2.94. So what we need to do is we need to build another column here. That's going to be our x minus mu column. Then after that, we're going to build another column. Well, maybe that was a little too. There's that column that we need, right? Then we need another column called x minus mu squared column. Remember that, how we used to square. Then we're going to do that. We're going to get the x minus mu squared times p of x column. There's that one. Ooh, so we're going to do a lot of building here. And then eventually we're going to have to add those up because that's what the formula for variance is all about. We're good. So if you want to start it now, go for it here. I do have another slide that has all the numbers there. So we go. Go with that here. Let you guys catch up first, then we'll go on to the next slide here. So if you know, and then if you want to keep on going here, so let me do the first one here. So this is going to be x, which is our score, not our probability, right? So this one would be 1 minus 2.94. That's what we want here. That's going to be the x minus mu value. So if you want to stay ahead of me here and do the same thing for all of them, you'll see a little pattern happening there. Then we're going to square each one of them. And they're going to multiply this column here, the probability column, with the previous column that we just made. So those two get multiplied together. And again, if you have a calculator with you, you want to try it yourself, go for it. All right, let me build it out. Let's see if we get the same numbers here as you guys are trying it yourself as well. So here's my x minus mu column numbers. Tell me if you guys get the same thing I did. So 1 minus 2.94 is going to be a negative 1.94. Then if we subtract 2 from it, 2 minus that just gives us, notice it just changes by 1, right? Because the x values go up by 1. This one, 3 minus 2.94 just gives us a 0.06, which is the positive value this time, because our average is a little lower than the 3 value on our survey. And then these guys should go up by 1 at this point, because we're going to go 4 minus that, just get tax on an extra 1. 5 minus that, just tax on a 2. Okay, so there's my x minus mu column. What do we have to do now? We have to square it. So next column up. All right, you guys try the numbers yourself as well, just to make sure you got it. Also notice that you need a parenthesis around the negative 1.94. Or what you can do, if you don't put a parenthesis around the negative 1.4, if you just kind of punch this into your calculator like this, you would have got a negative 3.764. And that negative is what we don't want. And so if you put a parenthesis around that right there, that parenthesis now is kind of swallowed up within the square. So that becomes positive. Or another way to do it, guys, talk about this here. If I know I'm going to get a positive answer out of it anyways, right? Do I even need to put in down the negative? If I were doing this, I would just say, look, I'm going to take 1.94. I'm going to square it because it's going to give me the same exact number without the negative there, right? Since I know I'm going to get rid of negatives anyways, I might as well get rid of the negatives initially and do that. But if you want to keep the negative there, just kind of for data's sake, that's fine too. Just put parentheses around there. Okay, and then tell me those numbers. Oh, here first. And what I got for the next column, here's what I got. So squaring those values, I get this. And then now squaring those values that are there, multiplied times the probability of each one of them occurring. Okay, add them up. And voila, I get something called variance. 1.6164 is what I got.
This is a test of the WHCC emergency messaging system. This is.
All right, those that are watching the video, this is October 21st. So over the loudspeaker, there just came a drill for the great shakeout. And so I wanted to stop the video for that purpose here. So now going on with the rest of it, the square root is just going to be, so the standard deviation is just going to be the square root of variance. I'll let you guys try that right now. Okay, so here it is. Standard deviation is just going to be that right there. You do want to go out a few decimal places of accuracy. Eventually what we want to do for standard deviation is we want to go about maybe 1 or 2 decimal place accuracy. So for variance, you probably want to go 4, maybe 5 or 6.
The WHCC
CC
Okay,
Great
here's
Shakeout
the-
exercise has ended. Thank you for your participation in our drill. You may resume normal campus activities at this time.
Okay, sounds good. I did not know there was going to be an end to it, so, okay. All right, talk to me when you're done, if this makes sense. And then let's talk about standard deviation. What do you guys remember about standard deviation? Well, the first time we talked about it was in chapter. We talked about like this little guy right here, is that right? Remember that? And we said if you go away from the mean, one standard deviation this way and one standard deviation this way, how much data do we have here? How much data is there?
I feel like
Mm-hmm. That's okay.
it was like 20 something.
It's okay. I'll give.
It's somewhere around 23.
Oh, cool, cool. Okay, got it close there. This is 34 on this side
Oh.
and 34% here. So we say roughly 68% or 70% of the data, right? If you're going to go really, really average. So there's about 68% of the data is contained within the first standard deviation of 1 going to the left and to the right. So we could say most of the data, right? Most of the data is just 1.3 away from the 2.94. Right? So 70% of the employees rank right in here. That's a pretty good sum. Could we go higher? Absolutely. We'd go 2 standard deviations away. We'd go 3 standard deviations away, right? And encompass more people if we do that. Okay, are we good there? Was that a good practice with mean, variance, standard deviation? That's just one practice item there with it. Okay, we're going to change gears real quick, and we're going to go to something called expected value. So expected value, as you guys write down the definition, is actually something if you ever played the lottery, that is what we've done. If you've ever been in a raffle ticket where you pay to get in, and then there's a payout or a reward afterwards here. All right, the other thing, the formula for it. Here's the formula for it. So now what we do, instead of using P, what we do is we use E for expected value. Expected value of X is mu equal to the summation of X times P of X. Okay, we'll see what this means in just a bit here, but this technically is the lottery. This is what you could expect to get if you play for a certain reward. There's a math instructor here on campus. What he does is he plays the lottery whenever the lottery goes, I think it's 375 million. I have to check that out again. So when he goes beyond that, what he does, he always plays the lottery because he says, okay, at that point, the expected value is positive, which means the probability is that I could win as opposed to lose. Has he won? No, he's not won. But for him, the expected value was, I think he calculated it one time in stats class, 375 million. Be fun to calculate that for us. Yeah, I see. Okay, for us, it's just going to be a raffle. Not $375 million, but maybe like a $500 prize. So let's see what we get to. All right, got some people still writing it down. Go for it, and then we'll do the example. Okay, let's do the example together. So here it is. Here's what I got. I got a raffle. There's going to be 1,500 tickets that are given out. They're sold at $2 a piece. And there's going to be 4 different prizes. There's going to be a $500 prize, a $250, a $150 prize, and a $75 prize. So then what you do is you buy 1 ticket. So question, by buying 1 ticket, what's the expected value of this game? or this raffle. And then we're going to interpret its meaning here. Because technically what we're really doing is we're just actually getting an average of all possibilities. Okay, so let's kind of put things together here. So $1,500, 1,500 tickets. That's all. So it's a limited raffle. And usually those are it right there because you don't sell, you only print out 1,500 tickets, right? Then you just assume that you actually, people bought all of them. Okay, so expected value, here's it is. If I were to gain the $500 prize, the question is, how much money did I actually gain? That's the first question. So we talk about the gain here. To find the gain of each prize, the $500 ticket actually has put $498 in my pocket. True? But I spent $2 to play the game in the first place. The $250 prize gives me $248 in my pocket. $150 prize again, $148. The 75 gives me 73. And then what happens if I don't win at all? I lost $2. So there it is. Don't win the prize at all. Your gain is -$2 in this process. We good? Since I bought one ticket, here's what we want to do. We want to make a probability table. Probability table says right here, my gain for the 498 is 1/1500. For the 248, at 498, right? 248 is again the same thing, same thing, same thing, same thing. Now this one right here at the end, right? Because there's only these many prizes, right? So I could lose 1,496 times out of the other one. So the formula says my expected value is add these guys up, multiply and add them up. So if I do that, here it is. I'm going to take the first gain, multiply it times my probability of winning it. Take the second gain, multiply by the probability of winning that one, third one, fourth one, and then of course my -$2 and all my probability of getting that one. Adding it all together, I get myself a $1.35 negative. Oof, okay, so what is this? On average, right, I can expect to lose $1.35 for this particular raffle. But it's just the fact that I could possibly win, right? That attracts human beings to play in the first place, right? But I could get the $500. And so we play, right? There's a book in the library, it's an audio book at West Hills College. Then it says, irrational, I think it's about irrational beings or irrational rationality, meaning like we as humans, right? We think like, yeah, we're very rational people, right? And the book explores this whole concept of how we're sometimes so irrational, right? It does not make any sense, but yet we do. So this is part of it right here. If you look at the numbers, if you look at you are expected to lose $1.35. But what are we gonna do? We're gonna buy those tickets, right? With the expectation that maybe I'm gonna be the $500 prize. Okay, so that is the end of 4.1. Oh. Okay, class, and then we're gonna begin 4.2 today. So binomial distributions. So what in the world here? So remember chapter 4? Don't forget chapter 4 is about discrete distributions, right? It's things we can count. It could be a survey where it's a 1, 2, 3, 4, 5 personality trait survey. So what does a binomial mean in terms of a statistics class, a math class? Binomial just means you have two options. So cafeteria food, did you like the food? Did you not like the food? There it is. There's a binomial answer to that. Yes, no. So sometimes we do have a two-point survey that we do in the college, and that's exactly what it is right there. It's just a yes or no. And we normally talk about success or fail. That's kind of what we talk about in terms of statistics. Okay, so let's go. So first things first, the conditions again. So here's my conditions. Again, don't need to write these down if you don't Want to, a lot of writing over here. And then we have our variables, and then we'll go on. So experiment has to be repeated a fixed number of times. So it repeats it. Each has to be an independent variable. So the probability has to stay the same. Oh, look at this. Here it is. Here's what makes it a binomial. So instead of being a discrete list of a personality traits, 1, 2, 3, 4, 5, now here it is. Only 2 possible outcomes. Now we got ourselves a binomial distribution. And the way we measure it usually is a success option and then a fail option. Success is what we want the probability to be. Failure is the opposite. Because they're independent trials, the probability has to be the same. And then we have our variable. Our random variable X is just going to be the number of successful trials. Okay, we're good there. Okay, and then next is all the variables we're going to use. So another page. Sorry, guys, one more page of kind of like the last time we did. Okay, and I just highlighted it real quickly here. This is notation. These are kind of these 2 slides. The one previously and this one probably should be written down. It'll probably help, as you know, go back to like which variable is that. So N is just the number of trials that are repeated. And the totality of it all. P is the number of probability of success at every single trial. Q is actually the probability of failure at every single trial. And then X, it represents the number of successful trials only. So X is what we think through when we do these. All right, now that we're done, let's try some here. Okay, this is again an example. Let's talk about it, talk it through. And then we'll kind of jot down a few numbers later on about it. So let's go with the beginning of it all first. First things first. This one, first tell me if this is a binomial experiment or not. Does it fulfill the criteria? If it does, can you name for me the variables and give me the number for each of the variables? We're good. So let's go for it. A certain surgical procedure has an 85% chance of success. A doctor performs a procedure on 8 patients. The random variable represents the number of successful surgeries. Cool. What do you guys say? Yes or no? So criteria number 1, is it repeated with a fixed number of trials? Yeah, I think so. 8, right? He's going to do it 8 times, right? He doesn't do it forever, right? Just 8 times. Here's your 8 times. Is there only 2 possible outcomes of interest? Yeah, it's either going to be successful surgery or it failed, right? Criteria number 3, is the probability the same for each trial? Yeah, this procedure is 85% success. And then the random variable X is going to count the number of successful trials for us. Absolutely, that's exactly what the random variable is. Awesome, it fulfills it. Okay, cool. Now, can you guys give me? So let's go back to here. This is the next slide we just talked about. So if you want to see it, yes, it is. Okay, each trial is repeated. Only 2 possible outcomes. The probability is given here, and X counts successful surgeries. We're good. It fulfills the 4 criteria of being a binomial experiment. Perfecto. Can you guys give me, what is the N number? 8, absolutely. That's the number of trials that surgery will be performed. We good? The P value, all yours. 0.85 is perfect. 0.85 or just 0.85 is cool. The Q value, for probability that the success surgery is going to go wrong. 0.15, just 1 minus that, or technically if you think about 100% minus 85%. Cool. And the X is going to be any number between 0. Remember, we're not just going 0 to 8, right? We can't say that. We have to actually individualize it, right? Because you can't have 1.2 surgeries, right? 1.4 surgeries. So X could be either a 0, 1, 2, 3, 4, 5, 6, 7, or 8. That's kind of what we're doing here. All right, on the next slide, I have it. Just kind of all spelled out. There it is. If I put in the other things.
So for X, to like list it out. Like
So
for-
you,
Yeah, so for X, to list it out for like the possible surgery that could be successful.
yeah,
Part of the probability.
a part of the setting up of the problem. Now, what we're going to do is usually we're going to choose our X out of that list. So we want to know what's the probability of the surgery be successful 4 out of the times. So then we choose that X being 4 later on. Okay, that's cool. We good there with that one? So once it becomes a binomial experiment, we pick our variables and we're good to go. How about this one? Talk to me about this. Tell me if this is a binomial experiment, yes or no. Give me NPQ and X if it is. So we got a jar. Jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. And what you do is you take out of the jar, you take 3 marbles from the jar. And then you've got this important word called without replacement, right? So what happens is when you take it out, we look at the color and we set it on the desk. Then we take another one out, look at the color, set it on the desk. We take another one out, set it on a desk. That's without replacement. Is this a binomial experiment? Has a few things. No, go ahead. And which criteria does it mess up on? So let's go back to our little list here. Number one criteria is the experiment is repeated for a fixed amount of number of trials. Is that true? We're picking 3 times, right? Then they get this little second part. Let me kind of jump back to this. And this is kind of where we think about here. So this is our definition right here, right? Boom, boom, boom. So is it a fixed number of trials? Yes, there are 3 trials, right? We're going to do 3 trials. And now where it is, look, each trial is independent of the other. Are these guys independent of it themselves? They are not. Is that true? Because if you do something without replacement, you're going to take it, right? And your probability has changed now, right? So they are not independent events. So it does not fulfill number 1. Okay, are there 2 possible outcomes of interest for each trial?
It's like 0.
Let's see, what we want to look at is if we're picking out a red marble. That's our question. So actually it fulfills number 2. Number 2 is fulfilled. Our success is picking out a red marble. Our failure would be picking out the rest of it. So number 2 criteria is okay. Is the probability of success the same for each trial? So once that is done, that is done. Are we good? If they're not independent trials, that means they're dependent trials. And we get ourselves, that is not going to happen anymore. The random variable X counts the number of successful trials. That's still good. Yeah. X was counting the number of red marbles. So that fulfilled it. So just criteria 1 and 3 have been dashed. We good? Okay. Just want to kind of make sure that that's set in our minds here. So this guy, because of this, really it's because of this right here. It's without replacement. If we looked at the color, right, and put it back, then it would have been a binomial experiment. But just because we took out the marble and we set it on the table, that's what made it not a binomial experiment anymore. Just that little piece there. Okay, so it failed because probably selecting the marble in the first round would have been 5 out of 20. But then because the marble gets placed on the table, it is no longer 5 out of 20. So therefore, the trials are not independent, and therefore this is not a binomial experiment. Okay, so we got the contrast there. Let's look at the formula now. So we finally got to the formula section. Here is our formula. The probability of success of a binomial probability distribution is we plug this into a formula. Okay, then obviously each of these guys have to be, we already did it before, so I don't want you copying them down again. But we do have variables here. So N is the number of trials, P is the probability of success, probability of failure is Q, X is the number of N trials. And so, but we already wrote these down earlier, so I did not highlight them. There's no need to highlight. Of the formula itself, obviously, you do need to write down. The way PowerPoint highlights, they don't allow me to highlight the formula. It doesn't think of it as text. That's why it's an image, so it doesn't allow me to highlight it. But we already have what N, P, Q, and X are already. We already wrote those down. So if you want to just write down the formula itself, formula looks pretty complicated. It is pretty easy. So let's go through one example through this and let's see where we're at after that. All right, back to surgeries. Here it is, rotator cuff. And let's kind of just think about it as we do it, and then we'll go into the. So if you want to maybe put down example 1, just put rotator cuff surgery, 90% success. So this is actually, looks like a source says Orthopedic Center of St. Louis. So that's kind of cool. That means that they keep tabs on how things went well. So here it is, 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 of those patients. So we have 2 successes, 1 fail. What should we do? Okay, let's go with it here. So one way that we could do this is by a tree diagram. And now we are introduced all the way in chapter 2. So let's do this. Don't do this way. This is the long way. So, but let's talk about it because it's the way we do it. So make a tree diagram and eventually use the multiplication rule if you need to, or the addition rule of each of these pieces here. So let's go with it. So we have 3 surgeries. It could be success or fail. Second surgery, success or fail in each one. Third surgery, success or fail. So we're looking for 2 successful surgeries. So 3 successes is not what we're looking for. We're looking for 2 successes and 1 fail. Yeah, so we're looking for this one right here. We're good. So let's see. Success, fail, success. That's the one we're looking for. Success, fail, fail. Not what we're looking for. Fail, success, success. Yes. And then no, no, no. So then what we do is we figure out the probability. Each one is 9 out of 10 for success. Is that right? So then this guy has a probability of 729 over 1,000. Which is pretty high. That's pretty good. This one has a 9/10 times 9/10 times the 1 fail that we happened. And notice we get 81 over 1,000. And then notice we have 81 over 1,000 over here. And notice we have 81 over 1,000 over here. So in this case, you can actually add them all up. That's fine. Add them all up. Or you could just multiply by 3. That's fine. 3 times 81 would give us 243. Divide by 1,000 gives us 0.243. So about 24%. Okay, are we good there? That's the long way. Don't write this one down unless you just want to put method 1, tree diagram. But we normally don't do it like this. This is only like when you have like just really small amounts of data. It gets too complicated to write a tree diagram. Sometimes we do go back to check our work sometimes. If you really want to just kind of delve into like, why is it wrong? Why is it wrong? What's going on? What we want to do is we want to do it by formula. So formula, let's go with it here. So we have use a binomial probability formula. Here it is, n is equal to 3. True. P's number of success is 9 over 10. And normally what happens in mathematics is that, especially when we use let's talk about this because this is important here to think through here. If we're going to do it by hand, we're going to write as 9/10 because it's easier to deal with fractions by hand. If we're going to do it by technology, it's easier to plug in decimal points. So let's do it both ways here. The book, and I'll tell you here, this is the way I used to do it when I was in college because we did not rely on calculators as much. In fact, the calculator did not even have a probability button inside it, as we learned last time. So, or teachers did not want to teach it that way. We had to do everything by hand. We multiplied everything out, we crossed everything out, and then we got our answer. So let me do it the way I used to do in college, and then we'll jump to the calculator mode here. Here's the way I would set it up. What's the probability of having 2 successful surgeries? Now this guy right here, that guy is 3C2. Are we good? That's from the formula right there. What the textbook wants you to do is keep these in. Keep these in fraction mode because it's a lot easier to cancel top and bottom. That's why. So on top, notice that 3 minus 2 is just going to become a 1 factorial. Are we good? So if we kind of want to write it this way, and then we'll do the technology piece to it. Let's kind of do it slowly just so we get the, I do want you guys to learn the math behind it because that's important as well. So this guy is 3C2, 3 on top, 3 minus 2 over here, and then the x value factorial. Well, 1 factorial is just going to give us 1. That goes away. So what we have here is we have 3 times 2 times 1 on top. This becomes 1 factorial, which is just 1 times 2 times 1. Okay, so notice what happens here. The 2's are gone, the 1's are gone. It's 3 over 1, and that's how the 3 gets over there. Okay, we're good there with the 3. And notice we're kind of getting the same numbers, aren't we? Notice the 3 we had before, because we had 3 different ways to get that from the tree diagram. This is the multiplication of 9/10 times 9/10, 81 hundredths. And this is just 1/10 to the first power. And so multiplying all that together, 3 times 81, or 81 times 1 is 81 still, over 1,000. And 3 times 81 would be 243 over 1,000. And then divide that out and we get ourselves our final answer. Hey, this is the same answer we got on the previous slide, true? So that's cool. So the numbers work out. Okay, so the direction that stats education is going is the fact that since we have more sophisticated calculators, we do it by calculator. So let's try to do this by calculator, getting the same answer. All right, getting out of calculators. Most of you guys have a TI 84. This is 83, but very, very similar the way they're set up. So here's what we're going to do. This whole concept of this first one with the factorials in it, we're just going to grab the combination button in our calculator. So let's go with it here. It's going to be the distribution piece right here, but we got to put in the 3 first. So put in the 3. We're going to go second distribution. Nope, sorry. The stat button right here. No, that's not fun. Where'd it go? Sorry, I went the wrong way here. So we're going to go to math right over here. Math, and we're going to go head over to probability. We're good. Probability, and we go to NCR because we're looking at combinations, right? All the different possible arrangements of 3 objects into 2 pieces here. So we go click enter, and then we're click on 2. So that'll take care of that whole factorial process in the beginning. So then let's go like this. Let's click on multiply right over here, multiply, because I'll separate this all out by itself. And notice instead of putting in 9/10, it's a lot easier just to put 0.9. 9/10. And then we have this little, it's called a caret button. It's right over here. It takes us into the exponent mode. So when you click on this one, the TI-84 is actually the change script, and I think they actually get you to exponents. Is that right? So 2, get out of the exponent, but if you have an 84 that has something called pretty print, you guys are sitting in the exponent button. So then what you're gonna do is you're gonna take this first arrow here, you're just gonna click on the arrow to go a little forward, that's all. That gets you back to your form where you're in. Okay, this one, we're gonna multiply it times. 1 divided by 10 is just 0.1. And we're gonna take that to the first power, which really just, if you keep it alone, you know, all numbers are taken to the first power, right? If there's nothing there. Anyways, I think we've got everything. We've got the combination in front, the success probability, the fail probability. Let's click enter and let's see what we get. Yes, we got exactly what we got on the previous slide. Are we good? In fact, on the previous time we did that here. So there it is. There's the calculator way of doing it. Which I think is a lot faster and better, because you guys are not going to be statistics majors, or maybe some of you guys will. So if you are, then you can practice the manual way of doing it as opposed to the technology way of doing it. Okay. There's that. Let's go on. Okay, so now let's go on to a full distribution now. So we want a binomial, which means yes or no, right? Probability, we want a distribution out of this. So listing all the possible X values according to each of the probabilities. That's what we're looking for. So this one we're not going to do because it's going to take way too long. All right, but an example here. An example would be, hey, let's do the knee surgeries again, real quick here. Different numbers here, but let's say a microfracture knee surgery, which means you got just a tiny fracture in there. I forget the exact definition of a micro fracture, but let's say n is equal to 3. We're gonna have 3 surgeries, and the probability of success is 75% or 3/4. So notice what we did is just like we did in 4.1, we made a distribution of all the different possibilities. So don't need to write down the example. And so remember, whenever we talk about distribution, we're just listing all the possibilities. Just like 4.1, we can make a distribution graph of it as well, right? But the only difference between 4.1 and 4.2 is it's binomial. So it's either success or fail at each one. Okay, so let's do an example here. An example as we go. Example, constructing a binomial distribution. Here it is. In a survey, US adults were asked to identify which social media platforms they are going to use or they use. Results are shown. So 6 adults. Oh, okay, I'm going to write that down. So six adults participated in a random survey and asked whether they use the social media platform of Facebook. So construct a probability distribution for, again, all all the number of adults who responded yes. We're good. So I got 68% of users. That's interesting. Do you guys remember? Do you guys even remember something called MySpace? Okay.
It sounds familiar. No, I've heard about it. Yeah.
Uh-huh.
But I don't know much else.
Gotcha. Okay, so it was the first social media platform to hit. I was in college at that time, so people were always posting into MySpace. You can go to your own website, and you pretty much can put pictures and stuff like that of you say. So then everybody that were trying to get on, put their name out there, usually had a MySpace account. And it was just pretty much pictures and whatever you wanted. I don't think there was any interaction between the two. It was pretty much just like your own website sort of thing. Anyways, let's go with it here. I think we're going to finish up with this one here. Making a distribution, making a binomial distribution. I have 6 adults participating in the survey. This is already a US survey. We good? That's the distinction. It's not 6 adults are giving us those numbers. It's those numbers already there. Now we're going to ask 6 adults if they use it. So if this is true of the numbers, what's the binomial distribution of them saying Facebook or not saying Facebook? So let's go with it here. See if this makes sense. The p-value of success is 0.68. That means the q value would have to be 0.32. Since we have 6 adults, there's 6 possibilities of success. And this one's big. Here it is, ready? We're gonna have to calculate each one of them at x equals 0, at x equals 1, x equals 2, x equals 3, and so on, right? Because we're trying to make a full distribution. And so here's what we got. So let's say of the 6 adults that we asked, 0 of them said I use Facebook. What's the probability of that happening? 0.001. Probability that one of them said, in any combination, right? One of them said yes. Probability that 2 of them said yes, that 3 of them said yes, that 4 of them said yes, that 5 of them said yes, and the probability that actually all 6 of them said yes. What's the highest probability here? Which one has the highest probability? Yeah, it looks like about, yeah, the highest one is 0.328, right? So we expect probably at least a third of the time, if we ask 6 random adults, they should probably say 4 or 6 should say yes. That's kind of what we're looking at. Okay, so then how do we actually make the distribution? Here it is. Eventually, I just use all these numbers again, and I bring it back to something looks like this right here. Does it fulfill a probability distribution? Back to 4.1. Are all the p-values between 0 and 1? Yes. Do they all add up to 1? Yes. So it fulfills a probability distribution. It fulfills a discrete probability distribution because it's just 0 through 6, right? There's no 1.4 people, right? Then it fulfills a binomial distribution because it's a yes or no answer. We good? Okay, I think with that, we'll stop for today. We'll finish it at 4.2 next time.